4 days, 9 safety experts, 13 presentations, one simple mission: to make diving safer. This is Dan at DEMA 2020. Safety seminars from the pros who know.
All right, good afternoon and welcome everybody. We're on the fourth and final day of DEMA 2020. Our virtual talks have been going well, and it's great to see you all here with us. My name is Steve Jamroz. I'm the Director of Marketing here at DAN. And again, we're thankful to have you with us today for Francois' presentation entitled Accident Review. Did your equipment fail you, or did you fail your equipment? In just a minute, Francois is going to discuss why equipment failures occur and what can be done to prevent these accidents. This session is going to be followed by a brief question and answer period. So as we're going through the talk today, please post your questions in the chat bar to the right. We'll make note of those and we'll get around to those at the end. But first, let me introduce you to Francois Burman. Francois is the Director of Risk Mitigation here at DAN. His primary responsibility is DAN's safety and accident prevention initiatives. He oversees DAN's recompression chamber network. Francois is the former CEO of DAN Southern Africa. He's a nuclear engineer and a hyperbaric engineer, so he knows what he's talking about. He's also the author of Risk Assessment Guide for Dive Operators and Dive Professionals. So Francois, thank you for being here with us today. I'm sure your presentation is going to be enlightening and informative. So let's get the presentation started. I'm going to turn it over to you, Francois. Thank you.
Thank you, Steve, and hello and welcome everyone to this presentation. Hopefully it won't be too technical for you, but for those of you that always ponder these things when equipment fails, I'll give you some clues as to what we see. Most often when we hear about an accident, or when you actually are involved in an accident and equipment is involved, our first thought is to go to, well, what went wrong in terms of, was it the manufacturer? Was the equipment just failed? Did I do something to damage the equipment? And as we go through a series of accidents that I've selected to discuss with you, you will see that we actually have a lot more control over the situation if we just remain aware of what can go wrong. The fact that we are relying on equipment, what we would call life support equipment, to sustain us while we're underwater, and we have a fairly significant responsibility to our own lives, and we should understand what this is, and doing that, we'll be able to prevent many of the incidents that we see happening out there. So, I can get the mouse to work. There we go. The question I'd like to try to answer, and as Steve introduced the talk, is ultimately who is responsible for the accident. And most accident theories that you'll hear about or hear when people present them or read about them, an accident is a sequence of events, and there is some degree of luck or fate involved in that. But most often there's several steps that if we could avoid or remove one of those steps from the process, we're highly unlikely to then result in an accident where somebody gets hurt or equipment actually fails on us. But failures do happen. So even though we know all of this, even though people are trained, the equipment is properly designed, and we should know what we're doing, we still have accidents. We have an incident reporting system here at DAN, so we are able to respond to things reported to us. And of course, we also look through the social media, look at the press, read reports, hear other people speak about accidents that they've gone through. And in the last 3 years, we've had 21 of these, we call them significant accidents, if you like, that we've become aware of. Obviously, there are many more that we aren't aware of. But these were enough for us to actually consider in terms of what caused the accident and how can we go about educating people or perhaps speaking to the manufacturers to prevent these from happening again. Because ideally, we want to make sure the diving remains safe. Yes, there are cases where the manufacturer perhaps has one or two shortcomings, but if you analyze the actual incidents and what went wrong, you'll find that the manufacturing flaw in most cases is really only a tiny contributor to the bigger picture. And when we because I certainly do, discuss these things with the manufacturers. If they need to make a modification, they consider that. Or in some cases, when these things tend to happen more frequently, they'll issue a safety notice, a recall, and they will obviously make design modifications to ensure this doesn't happen again. But actually, most of the time, we see that accidents happen as a result of either inadequate training or certainly skills that have diminished over time. People not taking care of the equipment, physically manhandling it or letting it lie around, or not having it maintained as it should be maintained. The manufacturers have good reason for giving you maintenance instructions. And then lastly, what I call complacency. You know, first time we dive, we know that we're underwater, we could drown. Clearly, you know, that's what happens in many cases. So we pay very careful attention to making sure our DV's in our mouth and we properly weighted and we follow the instructor and do what we're told to do. And the same with our cylinders. You know, if we're a dive professional or a filling station filling cylinders in the beginning, when we taught about explosions and things that can go wrong, we pay very careful attention to these things. But with time, we become a lot more comfortable. And what is actually happening in our perception is the risk is getting less. But that's not true. The risk remains the same. It's our perception of the risk that changes, and that's the trigger that normally ends up starting off an accident or an incident. Yes, we have to add that there are sometimes things outside of our control, and sometimes it's just bad luck. And you know, bad luck can happen early on in the chain. We can get away with things. You know, we can overfill cylinders many times, and nothing happens. And then on one day, if we've overfilled the cylinder, there's a crack, somebody drops something, and that's when the accident happens. So it's a sequence of events. So we're going to look at these incidents over the last 3 years. I'll just give you a brief rundown to categorize them, and then we'll go into some degree of detail with some of them. So when I look at risks, my traditional way of looking at anything in terms of a risk is, what is the equipment, the mechanical issue that we face? Is there a fire, an explosion issue? And then what are the human factors? What effect do these things have on people? So we've had a couple of filling whip incidents, certainly breathing hose failures. From the picture you see there, that was an article that we published in an alert diver, followed by another article, and you'll see, I'll talk about the third article, learning as we go along and not really coming to grips with everything as we try to puzzle through who or what caused these things to fail. Then we've had 5 first stage regulators. We hear a fair bit about these when you get essentially a free flow coming from the first stage. So we're aware of some of those issues. Then we've had 3 significant cylinder explosions, and I'll discuss one of them with you. In terms of fires, we've had 1 first stage regulator fire, and that's the one I'll discuss with you, and then 2 rebreather fires. And in all 3 cases related to pure oxygen that was contained in the cylinders. And then lastly, human errors, things that we do wrong as people. And there's one very sad case with a mismatched thread, and I'll give you some details on that. A slightly less significant one on a buoyancy compensator that failed, and then something that presents itself continuously. No matter how much we bring this to the attention of the diving world, we have issues with contaminated gas. And remember, again, you're down there, you get to a certain depth, and then the contamination starts to take effect. And we'll have a look at some of that information in a moment. So let's have a look at the first of our incidents. This happened just before DEMA last year. The person that it affected was a very experienced, let's call him a leader of the diving section at a university in the Caribbean, and filling cylinders is something he used to do every day, or still does every day, before the students get ready to go out and dive. And it happened to the filling hose. He was just finishing up filling a bunch of cylinders and something went wrong. So the hose itself was clearly rated for the pressure, 3,300 PSI filling pressure, and the hose was rated to 4,500 PSI, which means pressure tested to about 7,000 PSI. So it wasn't a weakness in the hose design, I should say. Service history, about 9 years in operation, which most cases it's a good time to start considering changing things, but by no means would we expect a failure. And he does regular visual inspections every time when he connected the hoses to the cylinders. He would check that there's no sign of any mechanical damage, but it failed. And it failed at the crimp fitting close to where the cylinder side of it. And obviously the free hose then went lashing out all over the show. And he was very lucky to actually not be struck by the hose itself. He did fall backwards and injure himself, but the wound you can see over there is an abrasion caused purely by the ejection of the high pressure gas. So the compressor was obviously still running to some extent, and there was high pressure gas in the hose, and it very narrowly missed his eye. I'm not showing you that particular picture. He says to me, it looks worse than it is, but I think that's enough stress when something like that happens to you. And he's concerned now, and we're talking of a couple of months after the incident, is he's probably going to have some permanent deficit in his hearing, because clearly when hoses break, the noise level is tremendous. Okay, so what would cause this? And it's a difficult one to answer in the context of many of the other examples I'm going to discuss with you. So yes, it could be fatigue, because, come back to this, we don't tend to support our hoses when they are being used to fill. And yes, potentially there could have been a flaw during manufacturing, but 9 years after the time is a long time, and thousands of fills with this particular hose. So one wouldn't expect there to be a manufacturing flaw. But of course, these things, sometimes it's a very minor flaw that then grows over time. So we can't really state with any certainty what went wrong, but we can certainly make recommendations as to how to either prevent it, or if it does happen, to put ourselves in a position where we don't get hurt. So on the technical side of it, clearly we need to make sure we use certified products from people that we feel we can trust, that have a good track record in terms of safe products. We want to maintain our inspections and perhaps look a little bit deeper when we do our visual inspection, when we're coupling up the hoses. If you look at the picture above there, no sign of any corrosion, so nothing that you would immediately say, hang on, this has been neglected. And he says there was no sign of the braiding coming loose at all. But a very wise thing to do would be to fit a whip restraint. And from where I come from, and I've had a fairly long history in not only recreational, but also commercial diving and diving equipment, these are compulsory in many industries. They're not compulsory in the scuba diving industry, but they're relatively low-cost items, and we can fit them to both ends of the filling hose. And if something does go wrong, or somebody opens something they shouldn't open, then it will contain that hose and prevent it from lashing around and causing any injury. And then very important for those of you that are actually filling the cylinder is to be aware of this risk. I know in the beginning when you fill your first few cylinders, you feel a little bit apprehensive, but months and months later, it's old hat for you, and you really are not going to pay the same attention that you did in the beginning. Always make sure you do visual inspections, perhaps bend the thing a little bit at where the joints are, just to make sure nothing's come loose. And most of all, if you don't need to be next to the hose or next to the cylinder during filling, then don't stand around there. So pretty basic stuff. Nothing we can really point a finger at, but again, it happened. Second one is an interesting one, and this is a follow-on from the articles we published in Alert Diver. It actually first started about 5 years ago now, when a colleague of mine actually she had an air out, and so she took the regulator out of her mouth, finished her dive on her octa, which we wouldn't normally recommend. And when she got to the surface, got back home, she pulled it apart, and lo and behold, we found these what we then called crystals that had clogged up in the hose and actually in her demand valve, in her second stage regulator. So we know about this, and we know it relates to inappropriate material selection during the manufacture of a series of braided hoses that did not come from Europe, and they weren't made here in the US. So we'll just leave that there for now. This person who reported it to me, I had a long discussion with him on the telephone, and we've exchanged many notes since then. Preparing for a cave entry, he was getting himself ready, took a breath out of his demand valve, and it was clogged. He got a mouthful of debris, which is pretty interesting in itself for the debris to actually migrate through the tiny opening that you have in a second stage. Anyway, he switched to his other regulator and found that he still couldn't breathe properly. So he surfaced, took the equipment apart, found that he had noticed before that his BC had inflated slowly, which was another good sign. And he had read our articles, and he knew about the failure of braided hoses, but hadn't really paid attention, doing his inspections as he should perhaps have done. We had 3 braided hoses. So both of his breathing hoses were braided hoses, and his inflator hose was made of braided hose construction too. So we have both of the demand valves clogged, and we have an inflator hose that is soft and squishy. So he, starting to put things together. When he inspected the hose, he realized that this thing wasn't working as it should work, or certainly didn't appear to be in the condition it should have been in. So the likely cause, well, we know about degradation of braided hoses, and this is what had happened to his DC inflator. But the mystery is, he sent his equipment to us, and I sent the hoses back to the manufacturer, because these were certified hoses from somebody that we work with. And they wrote straight back and said they've cut this thing into pieces. There's absolutely no sign of any degradation, any particles, any damage whatsoever. So that's interesting. He definitely had an air out. He had his mouth full of debris. So something clearly went wrong. And we could see clearly that the inflator hose had degraded with time. So it's now a mystery. And it is a mystery until we're sitting in my office, and I got a hint from a colleague out in the Caribbean who said to me that they'd seen some similar things before. So another colleague of mine in my office decided to experiment with this, and we attached the degraded hose to a regulator, the same as the diver was using. And we attached the breathing hose to the other side, and then I wiggled it around and let gravity do some of the work for me. And lo and behold, we got crystals coming out the other side. So what you can see over there, and I'll show you another picture in a moment, is the regulator that was used, but it's not unique. There are many regulators that have the same feature, but the gas goes through from the high pressure to the intermediate pressure stage, the hub at the bottom, and that connects to your breathing hoses, your inflator hose, your dry suit inflator, and it has a common area. So if one hose were to fail, in this particular case, degrade so that those pieces of degraded plastic start floating around, then when you get to the surface and you purge, you're going to get flow in the direction of the purge. So the particles will move from where they started from through the regulator into the other hose. Or when you're carrying your equipment, shaking it around, or just purely from gravity, these crystals can actually migrate. And I call them crystals because that's what they look like, but they're actually, in fact, just hard pieces of brittle plastic. So really important to do your inspections. In our articles that we published, we gave you some clues as to how to go about checking your braided hoses. They're great. They're nice and flexible. They take the strain off your mouth when you're diving, but one just needs to pay attention to them. If you buy the reputable types, after 2009, certainly we find that we haven't seen any significant failures. And I say significant because sometimes it's hard to actually tell when the hose was made. When you send your regulator in for maintenance, please make sure that the techs report anything that they find to you, especially if you're a bit concerned about things that weren't working as they should work. And lastly, be aware of what this issue is. And in the beginning, we suggested that maybe your primary breathing hose could be the flexible type, and then your backup, your octo, which you don't generally use, could be the rubber hose. But in this particular case, it wouldn't make a difference because those particles will pass through the regulator and lodge in the demand valve again. And just to illustrate it a bit more clearly for you, here's a cross-section of a regulator. We can see our high-pressure cylinder gas going in through a filter. So the particles can't come from upstream into the breathing section. Of course, you've got your pressure gauge also connected to the high-pressure section. Then we have our regulating of the pressure down to your intermediate pressure, and from there it gets distributed from a common area. So the pressure to both of your demand valves, your second stage regulators, and to your inflator hose, or if you have two, one for your dry suit and one for your BC, they all come from a common port. And it's not for us to say it's a design flaw, it's just a characteristic of how the design is done. And the degraded hoses have been a feature only for the last 5 years, and as people get more and more aware of them, they're paying more attention, but certainly something to be aware of. So practice your buddy breathing and make sure that you equip it. If something goes wrong with breathing, you have plan B. Okay, the next one is an interesting one, and those of us with aluminum cylinders you might call them, not from where I come from, is we obviously with time and certainly the presence of chlorides, they will start to corrode, producing a white aluminum oxide powder. In itself, not a big problem. However, in this particular case, the diver was on a liverboard in the Galapagos Islands, great place to be, and she noticed white particles on the inlet to her first stage. That was a bit strange, so took a toothbrush, wiped off the external particles, not realizing, of course, that there are particles on the other side of the filter. And she went back diving, and a few days later noticed the same. particles on the inlet. So where would the issue be, and now what is likely to go wrong? Well, that after her last dive, she woke up the next morning with no voice. She was coughing, her airways were burning when she was trying to breathe in, and she'd also developed an ear and eye infection, although we don't see a correlation between the things over here. So she returned home, went to see her doctor. He assumed it was a form of pneumonia, all the signs were there, gave her antibiotics, and 7 days later, her lungs were still burning. So there was something really, really strange here, and we got the report, obviously, after all this had happened. So, okay, aluminum oxide powder, we know it's produced in the cylinder. Powder in itself can be, right down from 1 micron up to 10 microns. Of course, they make aluminum oxide. You can make any size you want to. But the powder we see, some of it can migrate through the filter. Your inlet filter is good between 6 and 10 micron pore size usually. So if you take anything less than 6 microns, it's going to migrate through the filter as a powder form. And she had noted, I should have mentioned it on the last slide, that on the inside of her second stage, she saw this white powder. And we've actually had another case recently where it was a brown powder on the inside of the breathing regulator. This is a long-term accumulative effect. The picture you can see over there has happened over many, many, many dive cycles or pressurization cycles, and clearly not good maintenance. What we know from the medical theory, and I'm just going to quote it, I'm not your specialist in this particular regard, is that particles larger than 5 microns tend to irritate our upper respiratory tract. So that will be coughing, burning throats, and anything else that kind of gets stuck in the throat and makes breathing difficult. The particles smaller than 5 microns, which we know we get, and you can see that filter, the dirt on that filter, the oxide is on the inside, it's not in the inlet. When it's smaller than 5 microns, it accumulates in our lungs and the alveoli, making it difficult to breathe and causing an inflammation. So all the signs are there of regular pneumonia, and this one, short of another word, we dub it chemical pneumonia. And of course, those with some form of respiratory weakness are going to suffer even more. If you look at the standards that we set for particles, it's actually not very well documented. There's a lot of work has been done, and I actually published a fairly in-depth article in the last alert dive if you're interested in learning a bit more about this. And they usually clump it together with oil and other particles, so they're not very, very well maintained and monitored as time goes on. But generally speaking, we don't get dust getting through. So a real good clue is if you see any form of white powder, brown powder, black powder on the inside of your second stage regulator, please be aware that should not happen. Nothing should come down your breathing hose, and catch that in time before you end up with an issue. Clearly, things need to be serviced. And again, I put that picture up there for a good reason, poor maintenance. I don't know how many years of use that particular first stage regulator had. And then just 2 notes to add for you. A lot of things are said about aluminum oxide and people that work in aluminum factories and people that are metal workers with aluminum, that aluminum is carcinogenic, that it can be toxic, that it can actually cause Alzheimer's. But this is all anecdotal reports, and I've actually myself been involved on the Alzheimer's side with people working for me that then reported with this. But there's no scientific evidence to support this. There is scientific evidence to support some of the coatings that are used. So when people coat aluminium with chromates and phosphates and things, then we know that there is very much a toxic effect that can take place. And then interesting to see what the EPA puts out. So we know we've had these terrible wildfires in California. We know the biggest issue is not carbon dioxide or carbon monoxide, not from the distance where we're going to be, but from the smell, the smoke, which we smell and which basically contains particulates. So we know what levels of particulates are safe for people in factories and for people with respiratory issues and so on. But I want you to just bear in mind that for every atmosphere that we dive deeper, so when we go down to 33 feet, we're now at 2 atmospheres and so on, we double the amount of particles that we're going to be breathing in. The same as we will increase, surface equivalent value, increase with each atmosphere, the number of carbon monoxide and carbon dioxide molecules. So at the surface, everything seems fine. But as we start to dive and go down deeper, we're going to be breathing in more of these particles, and they're going to accumulate, obviously. Okay, here's a very sad case, and it gets played over and over again, and we just sometimes really difficult to come to terms with why people don't learn these particular lessons. So this one happened in Israel. We got some pretty good reports because one of our colleagues was flown over there to actually investigate what had happened. And I refer to these as the old aluminium cylinders. These were the LOA 6351 that was made up until about 1981. Big cylinders were made of this alloy because they discovered in the late 70s that there was an inherent sustained load cracking issue. And so they changed alloys. First of all, they instructed people to stop using it, and you could only use it under special permit conditions with additional inspection requirements. And then since 1989, they don't use this alloy anymore. In this particular case, the cylinder exploded while it was being filled. It took off part of the operator's hand and lost his hearing in one of his ears. He was just very lucky. If you look at the amount of damage on that cylinder, a couple of the fragments that went flying out. And if you look at the cinder block wall that I'll show you in a moment, you'll see that there was a bit of collateral damage too. It's not part of this discussion, but I'd like you to note the color of the inside of this aluminium cylinder. There's a big warning sign, but it's not related to this accident. Okay, so what causes these particular issues? We know about LOA 6351. We know that there's sustained load cracking. It doesn't happen in every single cylinder, but that's why you have a visual inspection requirement that must be done annually, and this is what they look for. Here you can see, hopefully it's clear enough for you. I can't get the mouse to work. You can see over here the, try it like that. You can see the crack running down over there, which we're trying to highlight. And all that requires is a degree of overfilling and some abuse, and obviously lack of inspection to pick it up before the time. And that day, after years of overfilling, abuse, physical abuse, we suspect lying in the sun for long periods of time, which over a long period of time will start to anneal the aluminium. Well, that was unfortunately the day that it happened. So we know for very good reason that the requirements are to do your visual inspection annually. We also want you to be aware of the 6351 requirements, and unfortunately, the cylinder is not marked with the same number of digits. So 6498 refers to the special permit issued by the Department of Transport. It's not the alloy of aluminium. The 3AL stamped above, together with that special permit, tells us that that's still 6351. Since 1989, all the manufacturers, the ones that we normally see that make these cylinders, are using the 6061 alloy, which doesn't have the weakness or the propensity to have sustained load cracking in it. And just to kind of fill in the last blank, make sure that when you get your cylinder, if it is aluminium, and I'm talking now more for the professionals that are doing the filling station operators, is look for the year of manufacture. Year of manufacture is after 1989, then we know for most of our cylinders it's going to be made of the right material. Okay, let's have a look at a couple of fires that have occurred and that we've managed to analyze to some degree. So this one was a very old aluminium multifunction regulator used in our resuscitator kits, and it was actually being used to train on one of the DAN emergency oxygen courses. Now you can see the aluminium one there. That was withdrawn from service many years ago and replaced with a brass multifunction regulator. So those of you that still have aluminium multifunction regulators, they're old, you really do need to replace them. I've seen boxes of these regulators at some of the testing laboratories, all of them having shown signs of fire on the inside. So they're doing the training. He opens up the first stage, the cylinder valve, and now the reports get fuzzy. And this is always, one of the interesting things in accidents. First-hand reports, witness reports, and then the reports that come in a bit later, almost as if people are trying to cover up for what they perhaps did wrong. And the first report I got said that there was a leak on the demand valve hose, which they then fixed by tightening up the hose under pressure, which in itself, not a wise thing to do. But there was a fire and it blew out the gauge. We don't even know where the gauge ended up. And clearly you can see that all the equipment has been burned over there. There was no sign of any maintenance done on this regulator. It was dirty. There were still parts of contaminants that hadn't burnt on the inside when they analyzed it. Both of the student and the instructor were burned, and the instructor particularly badly burned. So not something that we want to take lightly. Okay, when it comes down to causes of fires that relate to any oxygen application, we have three great pointers, or three parts of a triangle that we can identify and hopefully come to a better way of actually dealing with this. And that is, we need a source of fuel, so typically contamination. We need a source of heat, That's the part that's a mystery. And then obviously we are bathed in oxygen. We can't avoid that. Contamination, usually in these instances, is fingerprints, people touching the pin index valve on the cylinder or using the thumb to locate the seal on the actual regulator itself. Could be some inappropriate grease, could be dust. One doesn't really know. Difficult to pick up afterwards what the fuel source was. The trick here is the ignition source. What actually causes the fire to start? And we know with flow-related issues, we're either looking at flow friction, which means rapidly moving oxygen, but that shouldn't happen in this case because an oxygen cylinder valve is designed to limit the speed of flow through the line and through the parts after that. Particle impact and adiabatic compression are the two that we are more or less settled on as being the main causes of oxygen fires in our industry, in the scuba industry. Particle impact usually comes from inside the cylinder or could be dirt when the cylinder was last serviced. We don't really know where they come from unless they're on the outside. And adiabatic ignition, heat of compression as we call it, occurs in this particular instance when we open the valve too rapidly and the gas starts to move at great speed from the high pressure cylinder and then all of a sudden comes to a halt inside the regulator because the regulator is not flowing at this particular time. We cannot state with certainty what happened. We can't even state with certainty what the fuel was. We can see where it occurred, and then from there we have to add the elements up. But it can be avoided. Each one of these cases, there's been a human interface that has caused the issue. So very important to pay attention to the setup. If you hear a leak, whether it was the case or not in this case, please, if there is a leak, shut off the valve. Do not try to fix any leak while there's pressure in the line. Working with oxygen, keep everything clean. And again, we become complacent over time because things don't burn. And then one day they do, and then we track it back, and most likely we introduce the fuel somewhere. And then the rule with any form of oxygen is open the valves slowly. And I really mean slowly. And I'll come back and just re-emphasize that point in a moment. Okay, and clearly manufacturers study their products, or when they're doing the design, look at the things very carefully and decide which are the parts that need to be serviced. And they are very conservative, knowing that some of us abuse these things. So the service intervals that they recommend are really important. You can stretch them, sure, but it's when we stretch them or forget about them that things go wrong and we have our failures. Now let's have a look at a rebreather fire. I know there was one that they had in Bonaire earlier last year. This one happened to be in Mexico. They were doing cenote or cave diving. Very, very experienced diver. Again, in most of these cases I'm reporting to, I've personally spoken to either the person that was involved in the accident or some of the witnesses. So our information is pretty accurate, although, as I said before, witness reports tend to change with time. So he had a great rebreather, very well maintained. He knew what he was doing. He was getting ready on the land, still doing the setup, and the instruction is open the oxygen. So he opens the valve slowly because he knows what slow is, and there's ignition. So he was badly burned. In fact, on his face, both of his arms and various other places, but this particular hand was probably the worst. Significant burns. He was in hospital. Fortunately, made a great recovery with a minor degree of scarring left over, and very lucky because he was on fire before his friends around him managed to put him out. And of course, if you look at that piece of equipment, then you'll realize how hot these oxygen-fed fires can be. He was concerned because he's experienced, he knows about oxygen cleanliness, he knows about contaminants, and the only thing he could think of was that you don't travel with your oxygen cylinders for your rebreather. They rent them when they get to the dive destination because you can't travel with oxygen cylinders that are full at any rate. So he says to me, could it be some contaminant in the cylinder itself? And the answer to that is unlikely, because anybody filling oxygen cylinders knows about the hazard and generally are going to work very safely and very cleanly. The oxygen itself will certainly not be contaminated, but yes, it is possible that there could have been dirt or dust on the cylinder valve that got there from the transporting. Maybe that cylinder was left lying around for a while and accumulated some dirt. So perhaps particle impact could have been the cause. If you look at the filter, the inlet filter to the regulator, the top is what it should look like, and the bottom one is what it did look like after the fire. So clearly, there was some contamination, some dirt, some fuel in the filter, and the fire started very close to the filter. One would expect in this particular case particle impact. I don't rule out adiabatic heating for the reason that I really want to reinforce it for you and not perhaps in this particular case, because as I said, this diver was very, very well experienced. And you can see from the other parts of the regulator, significant burning all the way through, although there's not much melting on this because it's made of brass. And you can see the low pressure hoses failed catastrophically because obviously you get a rapid increase in pressure, which can't be managed by the regulator itself. So the general rules apply. Keep things clean. Make sure that whatever lubricants or sealants you use must be compatible with oxygen. Please, for those of you out there that think working with nitrox is not the same as working with pure oxygen, it's not correct. Most of the codes and standards, if you read them correctly, I'm not talking about industry information passed on, but I'm talking about the regulatory codes found in the CGA, the ASME, the ASTM, all the known regulations and included in OSHA. You just need to read it correctly. Is that anything above 25% should be handled as if it was 100% oxygen. And that means too that the parts, the components that you use need to be designed and compatible for use with oxygen. And then obviously limit anything outside of your control. If you have an oxygen system that you're diving with, you want to make sure that it never leaves your sight, leaves your control, and that you sure that it's safe. And then I come back to this one and I use the word slow again. We tend to think slow as well. I'll just kind of open the valve until the hiss goes away and then I'll open it fully. Well, in the industry, slow means 1 minute from when you crack the valve until it's fully open. And I ask you, how many of you actually follow that particular rule? And then when we have a stiff valve, the valve won't open and we strain to get the valve open. Then of course, rapidly the valve opens. And that's, again, one of the areas where these things are going to start from. Okay, the last of the categories is what we call the human errors. When I mean human error, gross human error related to equipment. So I'm not talking about training and other things at this stage. Another really tragic case happened in Belgium a couple of years ago. Easy to analyze afterwards. Hindsight is perfect sight or nearly perfect sight. But in this case, it was an aluminium cylinder made in Europe with a European metric thread. You can see the thread type there, 12.7 threads per inch. Good number to remember. 60-degree form, the angle of the actual thread itself. The valve was also a European valve, but it was the old imperial type, the 3/4 inch BSP, British Standard Parallel Pipe thread, or pipe parallel thread. In this case, 14 threads per inch. So for a given length of thread, there are more threads than there would be in the cylinder. In this case, a 55-degree form. I ask you, how do you get those two things to mate? And all I can tell you is I'm told that with a wrench, almost everything can be made to work. In this particular case, we don't know how long that equipment had been in service for, but the hose was being disconnected. And sadly, one of the rules we follow, right, is you don't stand over the cylinder when you're removing the filling whip. And there was a violent rupture. You can see there's a valve that has flown out the top of the cylinder. That's an accident that happened in Australia, but it's really just a good illustration for the valve physically shooting out the top of the cylinder. This particular case, I don't think the cylinder was full because there's not much movement in terms of where the valve ended up. And have a look at this great picture. I just hope it's clear enough for you. But you can see over here see the mouse is not, there we go. You can see the stripping of the thread, the damage to the thread, and with time, those threads are going to weaken. They're not going to be able to hold back the pressure. And on your unlucky day, it's been perhaps years that the thing's remained in service. It doesn't break immediately, but obviously with time, some degree of fatigue, filling and emptying the cylinder, maybe some heat, maybe some mechanical damage, and it flew out. And sadly, he was killed immediately. And most of the facility around there was destroyed. Okay, so what caused this? Well, as I said, hindsight is perfect sight. But we found out that they bought the valve. He was told to buy a particular type of valve because it's better than other valves. Well, I won't argue that one, but I don't think so. He bought it separately from the cylinder, and he had no idea of the fact that the threads are different. So he obviously put his things together, but now we're not looking at the diver. Now we're looking at the filling station operator, who clearly very experienced, had been doing this for many, many years, but this one must have slipped by and he just didn't check. Again, not that easy to check. We can see the material of the cylinder. We can perhaps figure out where it came from to then figure out what the thread type is. In Europe, the cylinders are marked M25/2 on the neck of the cylinder to tell you what the thread type is, and the valves are marked. So in theory, in Europe, you shouldn't make this mistake, but they do. So very important when you're filling a cylinder to be sure that the valve and the cylinder belong with each other. If it's rented equipment and it belongs to you, you clearly know that. But when you're filling other people's cylinders, these are things that you should be looking out for. In Europe, we get metric threads. We get the 25E, which is a tapered thread used in steel cylinders, and we get the M25, so easy to get those two mixed up. But the M25/2 is the parallel thread. Remember, 12.7 threads per inch, 60-degree angle, clearly marked on the cylinder. And here in the US, we use an imperial valve thread type, the 3/4 inch NPS. So again, we're getting from BSP to NPS, it gets pretty confusing. And in this case, we have 14 threads per inch and 60 degrees. So the only difference here is the pitch, the threads per inch that are obviously not meant for each other. And theoretically, they shouldn't screw in. But you know, when you've done it the first time and you remove it and the thread has been damaged in the cylinder, it's much easier the second time. And then you don't bother to actually inspect your threads. But knowing that that should be stamped on the actual cylinder, and I know it's not common practice, it should become common practice. The ISO standards are indicating we should be doing this, but very easy in that case to see that I've got an imperial thread on my cylinder valve and a metric thread on the actual cylinder. And then this is another good reason for having your filling area isolated, perhaps in a cage, a filling cage. Certainly, people that are not meant to be this be kept away from that area, and back to the inspections. Make sure as a filling station operator that you give your equipment that you're filling for other people a good inspection to make sure that you're not going to end up as this unfortunate individual ended up. One that's perhaps a little less serious, but certainly could have led to more complicated or more serious consequences. So we have a diver, rats. He tears his BC. So he has a 1-inch tear and he wants to go diving. Now we buy the patches. It's a nice piece of patch material with an adhesive, but he decides for whatever reason, it looks like it's not open properly. So he'll just fill it with the adhesive itself. And he goes diving and he's down at 45 feet of seawater, filling his BC, and the tear opens and he loses all his air in his BC. And as I said before, accidents are normally a series of things. So in this case, he was overweighted. He did manage to dump his weights, made an uncontrolled ascent, but was asymptomatic when he came out. So he had no physical symptoms, just some degree of pride when people found out what he had actually done and called him a fool. So, sometimes we do stupid things. Are there any of us that haven't perhaps climbed up a ladder at home and with an electric drill on our hand to drill holes in the wall? We've all done things, that are perhaps not that safe in hindsight. Okay, and then the last one I'd like to discuss with you today is the contaminated breathing gas. And this is a pretty scary one because some of the contaminants, certainly the carbon monoxide, we cannot actually taste or smell or feel or see. I mean, it's completely impossible to tell that it is contaminated unless you use an analyzer. This incident happened in the water. The diver was down at somewhere between 20 and 30 feet of seawater, down for about 6 minutes. His buddy, his wife, actually they noticed he looked like he had a seizure. He went up to the surface uncontrolled, got to the surface, clearly was lifeless. They managed to get the EMS in, so there were 10 or so minutes at least for them to get to where he was, and they resuscitated him. So much so that he called me about a month later or 2 months later to say, look, this happened to be, where do I think, is the issue? And just speaking to him on the phone, he said, I could smell this. The air doesn't smell that great, but, it wasn't anything that I didn't think that I could dive with. Big lesson to be learned out of that. So we had him send his cylinders off to be analyzed. They both came back with epic failures stamped all over them. So clearly the gas did not comply with the standards that are there for very good reason. So for those of you in the know when it comes to air quality testing, we know that the limits for carbon dioxide are 1,000 parts per million, carbon monoxide, 10 parts per million, methane, 25 parts per million, and odor, none. And have a look at what we found on this one of the two cylinders. Over 3,000 parts per million of carbon dioxide, but we can deal with that. And even at 2 atmospheres or 3 atmospheres, we can manage that level of carbon dioxide. Carbon monoxide, 500 ppm. At 2 atmospheres, that's equivalent to breathing 1,000 ppm on the surface. My only question was, how did he last 6 minutes breathing this contaminated gas? Methane is generally an asphyxiant, although it could also be a fuel. So at that level, it's certainly dangerous, but not in a short term going to be the cause of his issue. But strong odor, real clue. So if you smell anything, if there's any smell, if it comes out of the second stage, then take off the first stage regulator and smell the gas in the cylinder. If there's any odor, the gas in the cylinder, something is not right. And the second cylinder, a little bit more carbon dioxide, a little bit less carbon monoxide. You know, our accuracy in measurement or the resolution measurement allows for a couple of ppm either way. So basically, both of these cylinders have been filled from the same source. Okay, so clearly, if you look at the different types of contaminants, this is not a problem in the compressor. It's not likely a problem in the filters, because the filters generally don't remove carbon dioxide. So, you know, we're not expecting it to be absorbed. So the carbon dioxide is coming from outside. And even if this filter had been fitted with the carbon monoxide filter, the Hopcolite catalyst, those catalysts are designed to handle, you know, 20, 30, 40, 50 parts per million maximum. And after that, they cannot catalyze out all the carbon monoxide. 500 ppm after that filter indicates really very drastic contaminants. At that particular filling station, no record keeping of their fills, no history of air quality testing. So really not a great place. And someone else made the point, I think, on this one of the lectures before me. But if you're not sure about the quality of the gas that you're getting from a shop, for whatever reason, take the time and trouble to ask them to have a look at what goes on. Is it neat and tidy? Does it look like it's controlled, or is it filthy, covered in oil, covered in dirt, things lying around? Pay attention if there's an air quality test certificate up on the wall, that it's in date and that they at least are testing the air quality, which just means that they are paying attention. It doesn't mean that the air is safe, but it means that they're paying attention and understand that, you know, contaminants need to be protected against. So my first point to him was, please call the filling station. He didn't want to identify who they were. He happened to know them, and tell them, because if they're still filling air, you know, whatever surrounding conditions occurred, because this is unlikely to be the compressor or the filter itself, it's coming from something in the surroundings, that they know about it. And so they were warned, and they then, you know, moved the location of their compressors. And for all of us, gas should not smell bad. Doesn't mean that if it smells bad, it's going to have carbon monoxide. It doesn't mean if it doesn't smell, there isn't carbon monoxide. But unless you're very unfortunate, carbon monoxide is going to come with a bunch of other things. And in those other things, there's most likely going to be something that smells. So if the air does not smell right on your demand valve and your second stage regulator, switch off the valve in the cylinder, take off the first stage, crack the valve and smell the air in the cylinder, and make sure that it's not because your equipment's just been serviced. Maybe there's still a little bit of moisture on the inside, which you can then purge to get rid of, but you don't want any odor in the gas inside the cylinder. Okay, so just a couple of points to kind of bring all this home into a common place where we started from. So we have diving accidents that are caused by equipment failure. And the question is, why did the equipment fail? And we know in some cases, yes, there is a manufacturing issue, but generally very isolated. In terms of the hoses, we did reach out to the diving community several months ago with another Facebook posting, and we got a whole list of people who wrote in and said that they had very similar failures on the hoses. So we know about that particular issue, and we know what it is, and we can give you information as how to inspect against it. But it all comes down to awareness of risk, of training, of appropriate training, of remembering your skills, of not becoming complacent when you go diving. It's really important. That's why we have buddy checks. It's really important that you do them consistently, correctly, each and every time. And we don't just do a cursory glance to make sure, well, everything looks fine. Because it's the day that we didn't do the buddy check is the day that there was a problem. It's the day that our second stage wasn't working correctly and the buddy's octo wasn't working correctly. And that's where, you know, things really go badly wrong. So yes, equipment does fail, but most of the time it results from us not taking care of paying attention, being aware of issues. And when we cause the equipment to fail, it's generally based on ignorance, like not knowing there's a difference in the thread of the cylinders, or if we're at a cylinder filling station, not knowing that the old 6351 cylinders need to be inspected annually, meaning there should be a visual inspection indication on the cylinder that it's in date. It's thinking that we know it all. We've been doing this many, many times, and so we're completely in control of what the risks are. And at the end of the day, just a degree of stupidity where people should ask questions and they don't ask questions. So remember, the only stupid question is when the person doesn't ask the question, or the only stupid person is the person doesn't ask the question. And yes, the luck of the Irish might desert you on that particular day. You didn't get your 4-leaf clover. So there is bad luck, but in most cases, we could have avoided the bad luck. We could have mitigated the bad luck. And we can certainly take care of the cascade of events that happen after that by being properly trained, having done our buddy checks, having our buddy near us so that they can support us, and all the things that we are taught in handling equipment, in doing cleaning, and working in workshops, handling cylinders, and obviously in diving too. So please, we want you to take note of history. History teaches us things. I always say, the only thing that we learn from history is that we don't learn from history. And things happen again and again and again. Divers Alert Network, thanks to all of you that support us, we try to get that information back out to you through social media, articles we publish, Alert Diver, so that you can be aware of them. And it's that knowledge and that awareness that will help us all, both in the professional and in the recreational side, to avoid accidents and to dive safe. You do need to understand the risks, whether it's a chemical you're working with, whether it's oxygen in a cylinder that needs to be handled very, very carefully, whether it's the diving equipment itself, understand what the risks are. We weren't made to live underwater. If things fail underwater, well, we're going to be on the wrong side of any survival techniques unless we've, got backups in place. Follow training and practices, again, whether you're the recreational diver or the professional that is taught how to fill cylinders, how to take care of compressors, how to manage oxygen cleaning, and stick to those practices. Don't become complacent. Discipline and awareness are really key to avoiding accidents. And finally, heed the manufacturer's instructions. Make sure you understand the manuals. If you're just a user, make sure that it is maintained correctly. Very unlikely, very infrequently that a service center is going to be the cause of an accident. We do know it happens. Failures have happened when equipment hasn't been serviced correctly. Sometimes that's just your bad luck. There's not much we can always do other than, again, this is your life support equipment. If you're taking that down with you, if you're buying the hose whip that is going to contain 3,300 or 4,500 PSI of gas in it to fill cylinders at your dive shop, you want to make sure that it's bought from a reputable supplier, it's properly stamped, it's marked with all the coded markings you require. CGA and DOT will tell you what those markings are. We need to pay attention to them for very good reasons. So I've covered a fairly broad scope of things, and the intention is not to scare you other than to make you aware that we need to bear in mind a clear understanding of the risks if we want to be able to make sure we don't get on the wrong end of an accident. Please, if you have any questions, we have a dedicated email address, riskmitigation@dan.org. We welcome your questions. We've had an influx of questions over the last several months, mostly related to disinfection of equipment, as you can imagine. And now it's going back to other forms of incidents and accidents. I assure you, we answer every single one of them. Whether you think it's a stupid question or not, we will give you the perspective that we understand and certainly be able to point you in the direction if you do need to take any steps to then, fix whether it needs to be fixed or get the information that you're required to get, or just understand what has actually gone wrong in that particular case. And I'd like to end the way that most of the other speakers have ended, to extend a personal thank you to all of you members out there. We rely not only on your membership dues, but on your support, on your interest, on your questions, on sharing things with us that we can then learn from them and we can share that information with other people. So thank you for being supporters. I can assure you that your contributions are fully appreciated here at Dan. We put those funds to really good use. We take things very seriously when it comes to equipment failure and to dive safety. So again, thank you for that. And having said that, Steve, I'm ready to take any questions.
Great. Thanks, Francois. Really great presentation, interesting examples, and hopefully everyone took a little something away from this. We've got about 3 minutes left to take a couple questions. Like Francois mentioned, if we don't get to your question here in the next couple minutes, it's riskmitigation@dan.org. You can reach out to us anytime. We'll make sure to get that question answered for you. But we do have one closing presentation at 3 p.m. Dr. Tillmans will be talking to us, so we've got only a couple minutes here, so let's get started. Got a question from Nick. This one may need some clarification. He asks, going back to your first example, did the facility have a life for the cylinder whip Was the hose check fitted to the hose, is what the question says.
Okay, was the check valve fitted to the hose? In that particular case, no, because he had a valve that he used to isolate the gas so that you couldn't get, once you uncouple the hose, you could be sure that there was no gas in that section. Check valves are required, but, practice has changed, and recreational diving is not policed. We are certainly not the police. So yes, people aren't always aware of what they're dealing with, and they generally don't have accidents. In terms of the age of the whip, it was coming up on 10 years, and he thought at 10 years he'd probably just, send it away for some inspection. So this preceded him. 10 years is a good number. If your hose whips are older than 10 years, they really do need to be either replaced or at least hydrostatically pressure tested to 1.5 times the maximum working pressure, because that will most likely rule out any latent flaws or anything that is perishing in the hose. So that's a great question. It's a two-folded question. They do have a life. Having said that, I know whips that have been out there for 50 years, but that's not a good excuse. They do need to be checked, they do need to be inspected, and 10 years is a good indicator that unless you're going to do some serious maintenance, it's time to change them out. So good question.
All right, great, Francois. We've probably got time for one more question. This question is from Samari, and the question is, what is the optimum position to store a cylinder in, upright or laying down? And then for long periods of storage, how much air would you recommend leaving in the cylinder?
Okay, so we have two questions there. And the first one I'll preface with saying, if you store it upright, please just make sure that it is safe, that no one can knock it over. So let me talk to you from an engineering point of view. When cylinders are designed, they're designed with a thicker base so that if there's any moisture inside there, it's more able to handle corrosion before it actually leads to a failure. So from an engineering point of view, cylinders should be stored in the upright position unless they are empty and we know there's no moisture in them. So if they're empty, the valve is out and they're dry, then you store them on their sides. If they have gas inside them, they could have moisture, then the correct way to store them from an engineering point of view is upright. But I say again, it needs to be secured because you just need to knock that cylinder over if there's pressure inside it, hit the valve against something, and will obviously cause a big issue. And then the second question was how much pressure to leave in the cylinder. Well, ideally it would be empty, but that's not wise because if it's empty, then we can have moisture getting back inside there and causing corrosion. So 15 psi would be a really good figure to use. It's enough to prevent anything going inside. It's enough to prevent leakage if you have a really cold day and a really hot day and the cylinder expands and contracts. It's certainly going to be resistant to that. It'll keep things dry on the inside, and it certainly won't add to any reduction in the life of the cylinder. If I can just, Steve, you can just give me 1 second to add to that.
Sure. It's
not good practice to store cylinders for long periods of time full, because especially in aluminum cylinders, and especially if it's exposed to any degree of heat, it's essentially going to cause some degree of long-term strain on the actual material, and especially if there are other factors such as previous heat cycles or cracking or other abuse, it's going to end up in a weaker cylinder. So great question. If you're storing cylinders, if you're not going diving for a year or whatever, look, after a year, you're meant to have emptied the cylinder, had it visually inspected. But if you're not going to dive with your cylinders, get it down to about 15 psi. And remember that when you do go diving again, it needs to be visually inspected before it's then filled. So thank you for the question.
Great. Thanks, Francois. And with that, we really need to wrap this session up. We have one last closing session at 3 o'clock, basically starting now with Dr. Tillmans. It's going to be Listen to Your Heart, a cardiac health research update. You can find that link on the DEMA website and also in the DAN program manual. But thanks again. Thanks to everyone for coming to support us. Thanks for everything you do to keep DAN going and keeping us and able to develop the safety content for you. So we'll see you on the other side. Thanks for coming. Frauke Tillmans coming up next, 3 o'clock.
4 days, 9 safety experts, 13 presentations, one simple mission: to make diving safer. This is Dan at DEMA 2020. Safety seminars from the pros who know.